What if you had the perfect cheat sheet for any situation? Not some complicated long-term strategy, but just a simple guide telling you the absolute best move to make, right here, right now. Well, that's the whole idea behind one of reinforcement learning's most powerful tools, Q-learning. So let's dive in and see how this ultimate cheat sheet actually gets written, one move at a time.
So think about this for a second. How do you get an AI to master a game like Breakout, or even something way more complex like a robotic arm? I mean, it can't just read a rulebook and plan out its next 10 moves. It has to learn everything from scratch, just through pure trial and error. And that is the exact problem Q-learning was built to solve. You know, most of us, when we think about strategy, we think of a map, right? A complete plan from start to finish. But Q-learning flips that on its head. It's all about learning without a map, and instead focusing entirely on the immediate value of every single possible action. And the secret sauce here is something called the Q function. This is that ultimate cheat sheet. For any situation you're in, like, say, a specific screen in a video game, the Q function just gives a score, a Q value, to every single action you could take. A higher score means a better long-term outcome. It's really as simple as that. So in reinforcement learning, there are kind of two main ways to go about this. You could try to learn a really complex, high-level strategy, what we'd call a policy, that tells you what to do everywhere. Or you can take the Q-learning approach and just learn the value of each action. And what's so cool is that by just figuring out the best move to make in the moment, an optimal strategy just kind of emerges on its own.
Okay, to make this really hit home, let's walk through a super simple little thought experiment. We're going to build a cheat sheet from the ground up and watch as our little agent gets instantly smarter just by looking at the scores. All right, here's our setup, a simple little grid. Our agent can start anywhere in that blue zone, and its goal is just to reach the star. If it gets there, it gets a reward of 1. Anywhere else, 0. The challenge is, it has to figure out how to get that reward no matter where it starts. Okay, so let's say our agent starts with a really basic, and frankly, a not-so-great policy. Always move right. Now, if it starts in the top row, hey, that works. It'll eventually hit the star. But if it starts in the middle or the bottom row, it's just going to slide right off the screen forever and never get that reward. Yeah, a seriously flawed plan.
But now we can build our very first cheat sheet based on that flawed plan. And this is where it gets interesting. From the middle row, the action move right has a Q value of 0, right? Because it leads nowhere. But what about the action move up? Well, think about it. If the agent moves up, it lands in the top row. And from there, its always right policy actually will lead to the star. So boom, the action move up gets a Q value of 1. And this is where the magic happens. Just by looking at its brand new cheat sheet and picking the action with the highest score, the agent's policy instantly gets better. From that middle row, it now knows, hey, I should move up. It's a better plan, but you can see it still has no idea what to do from the bottom row. The cheat sheet isn't perfect, not yet anyway.
Right, so this isn't just a one-time thing. Improving this cheat sheet is a continuous process. It's a loop. So let's look at how this loop turns a simple improvement into an incredibly powerful learning algorithm. It works just like this. First, the agent just goes out and explores, messes around, and collects data. Second, it uses that experience to update the scores on its Q function cheat sheet. Third, it improves its own policy by just picking the actions with the highest scores. And then, it just does it all over again, and again, and again. And with every single cycle, that cheat sheet gets more and more accurate. So the agent keeps doing this loop, but how does it know when it's done? Like, when is the cheat sheet finally perfect? Well, it's perfect when it follows a rule called the Bellman optimality equation. All this really says is that the score for the best action you can take right now should be equal to the reward you get right away, plus the score of the best possible action you could take from the very next spot. When that equation is true everywhere, you've done it. You have found the optimal cheat sheet. But, and this is a big but, here's the catch. As this quote points out, that guarantee only holds true in simple little worlds like our grid. The moment you bring in the complexity of the real world and you start using tools like neural networks, things get unstable. The whole algorithm can actually fly off the rails with the scores just spiraling out of control. So how on earth did researchers get this working on crazy complex problems like Atari games? Well, they came up with a few absolutely brilliant tricks to make the whole learning process stable. These are the 3 big ones, and honestly, they're pretty cool. First up is something called the target network.
The problem is that your Q function is trying to update its scores to match, well, to match itself. It's like trying to hit a moving target. The solution is just genius in its simplicity. You just keep a frozen, older copy of the cheat sheet. You update your main network towards a stable, frozen target, and you only update that target every once in a while. This one little trick adds a huge amount of stability.
Next up, double DQN. It turns out that the basic Q-learning algorithm has a tendency to be a little, well, overconfident. It tends to overestimate its scores. Double DQN fixes this by getting a second opinion. It uses one network to pick what it thinks is the best next action, but then it uses a totally different network to evaluate how good that action really is. This little cross-check stops that optimism from getting out of hand and gives you much more realistic scores.
And the third pro tip is using what we call end-step returns. Look, learning from a single immediate reward can be painfully slow, especially if rewards don't happen very often. So instead of just looking one step ahead, the agent looks at the total sum of rewards over the next, say, n steps. This gives the learning algorithm a much stronger, more informative signal to update the cheat sheet with, and it can speed up learning like you wouldn't believe.
So what happens when you put all of these pieces together? When you combine that core idea with these clever tricks, well, you get some truly remarkable, almost sci-fi level results, where an AI can learn complex skills just by looking at raw pixels.
This is the famous breakthrough from DeepMind. By combining Q-learning with these stability tricks, their Deep Q Network, or DQN, learned to play old Atari games just by watching the screen. And it didn't just learn to play. On a whole bunch of these games, it achieved superhuman performance. But the real power here isn't just about mastering virtual worlds.
Take a look at this number, 96%. What do you think that could possibly be the success rate for? That was the success rate for a robotic arm that used Q-learning to teach itself how to grab a whole variety of objects it had never even seen before. This just shows how powerful this approach is, going from the clean, simple actions of video games into the messy, complicated, real world of robotics. And that's the crucial takeaway here. Q-learning, when you stabilize it with these clever tricks, gives us a way to create a single, powerful model that learns the optimal cheat sheet directly from experience. It totally bypasses the need for a human to sit there and design a strategy, and it finds the best moves all on its own.
This leaves us with a pretty fascinating question, doesn't it? We've seen this approach master games and robotics. So, if an AI can, in theory, create the perfect cheat sheet for any situation it's put in, what's next? What could it master?